Hi, everybody. Thank you for joining us today. I see people are still joining, so I'll give it another minute before we get started. If anybody has to get water or run to the bathroom, feel free to do so now, and we'll start around 1:03. All right. Welcome, everybody. Anybody new who has joined, welcome to our webinar today. We have a really exciting webinar on tunnel and vertical excavation impact on the surrounding structures for theory and practice. For anybody who is not familiar with our company, we are a subsidiary company of Midas IT. We develop a total solution service for bridge building, geotechnical, and mechanical engineering. These are some of the software that engineers most frequently use. Some of you might already be familiar with our bridge software, Midas Civil. Um, we also just launched Midas Civil NX, and we will be doing more webinars on that soon. For anybody who is new in joining this platform, or who hasn't joined in a while, this platform has had a little bit of an update. So I wanted to introduce some of the tools that you're going to be using today. So in the main screen, you'll find whoever is sharing their screen at the time, and up here you can see who is sharing their screen, whether or not cameras are activated. And then down here you can check your camera, your microphone. You can also check your settings. If you want to react or raise your hand during the session, you can do so using this hand raise icon over here. And on the top, you can ask questions to the speaker today. Um, we will do all of the questions at the end, so please feel free to submit them at any point. And then if you are having any trouble either with audio or with speakers, you can test them using the settings button. So today we have Ahmed Hussein. He's a distinguished professional in geotechnical and structural engineering with a strong track record of executing complex projects across North America and the Middle East. His consulting expertise spans multiple industries, including building infrastructure, marine energy, and dam sectors. Dr. Hussein has completed his master's and doctorate in the area of geotechnical and structural engineering, and his research focuses on generating sustainable and resilient infrastructure projects, which, uh, which withstand the uprising environmental hazards. So, Dr. Ahmed, I'm going to go ahead and give you presenter mode, and you can get started.
Thanks, Luciana, for the introduction. So, hi everyone. I hope you are seeing my screen. I'm just kind of learning my way here right now. So please feel free to tell me if you can't see my screen. So we are going today to speak about really exciting topic. It's about the tunneling and the vertical excavation impact. We're gonna take it from how it's in theory and how can we implement that in practice. So I'm not gonna top whatever Luciana said about myself. So I'm a geostructural engineering consultant. I've been working in industry for a while in executing complex project in the area of infrastructure, marine, and energy sectors. And I have been working also in research and also in the same areas. So I will be moving away from that. So in order to move to the agenda of today, we will be looking into introduction about why are we speaking about this topic, and also how can we calculate or study the tunneling induced ground deformation and the excavation induced also ground deformation. How can we employ the finite element analysis to calculate the ground deformation, and also what is the process to create a construction impact assessment that can ensure the stability and the safety of the adjacent structure. So in order to jump to the introduction, when we are looking at this picture, for example, right here, we are going over excavation, and this excavation can extend to almost 30, 40-meter deep below the ground level. And it can be horizontal, for the tunneling or cavern for an underground station. A lot of engineers and industry can be interested in how to make this excavation stable. But one of the other important areas that we should be looking at is how can we make sure that the adjacent structure, including building, residential, commercial, also the utilities and the railways around this area is also stable. Therefore, construction impact assessment due to excavation is one of the most important aspect of any project that we need to look into the safety of this adjacent structure. So the objective of this session is we are going to look into the theoretical ground deformation due to tunneling and excavation, which mean vertical shafts, and also how can we conduct construction damage assessment, and why and when we can employ the finite element analysis in this study, and how can we conduct a construction impact assessment and a roadmap for a comprehensive construction assessment. So when we are looking first into the tunneling, induced ground deformation, we can go theoretical into that, and there is a lot of research has been done in how we can get the ground deformation due to the tunneling excavation and come up with the greenfield calculation through creating this inverted normal probability curve. There is a mathematical equation that it has been thoroughly investigated, and we can create the inverted probability curve, and also we can also get the accumulated vertical deformation in the longitudinal direction, and we create the second deformation curve in the second picture. So both assumption, in order to develop that, as I mentioned, they are thoroughly investigated in the industry. However, we need to know what is really shaping this ground deformation. Two main factors are really important when we are really looking into creating these graphs. First thing is volume loss, and the second one is called the trough width. So let's look in deep. How can we come up with this deformation curve or this inverted probability curve? So we have a tunnel down here, and we are looking at the ground surface up there, we can see that like the ground surface is going to deform with a maximum settlement of S max due to the deformation of the tunneling or the reduction of the size of the tunneling down there. Theoretically, like we are looking into that the maximum settlement that will be happening down here should be more or less similar to the settlement that will happen at the ground surface. But in reality, that's not correct because of like many variability in terms of like of the ground deformation, compressibility, or any other things. Like we know that the deformation will not be the same as a tunnel here. We know that the maximum settlement will be happening at the tunneling area here, at the excavation of the tunneling. However, like this settlement will be reduced going up, and it will be the minimum compared to the tunnel at the ground surface. So there is like a mathematical routine that you can go through based on the maximum settlement that can happen in the tunneling itself, and to create like the inverted graph up here. So this is, as I said, it really depends in two main factors. The first factor is the volume loss, and the volume loss is the ratio of the additional volume excavated from the ground removed to the theoretical volume of the tunnel. So we basically look at the reduction of the volume in the tunneling, and we can come up with like this curve up there. The trough width is basically, we can see here into this graph, there is like a point of inflection. Based on this point of inflection, we come with like the size of I, and the depth to the head of like the tunnel here, we can come up with like the uh, trough width. So these two main factor, going over like this mathematical routine here, we can create like this graph, and we can start to come up with like this ground deformation curve that we can eventually use it like to conduct as a construction impact assessment. So how can we create like the, okay, now we already know where is the S max. In order to create or like come up with like the value of the settlement across this graph, we can apply simply in this equation, which basically depend on the maximum settlement that happened in the middle, and also like the trough width and the location from the tunneling itself. So by applying in this series of equation here, we can create this graph. But let's focus, like let's go back here for a second. We already know that this is kind of like investigated and fundamentally can be dependent on the soil type, and we also assumed here that the settlement that will be happening in the tunnel is the same as the settlement that will be happening at the ground surface, but that's not like utterly correct. Therefore, we like this can be like a starting point where you can do your assessment. So if we start to look into the vertical excavation induced ground movement, there is a lot of theories that has been put here in order like to come up with like the ground deformation curve. That depend on many factors. For example, if our shaft was circular, some research has been done here. For example, New 2017 has conducted some research based on circular shafts that happened in the London airport, and start to document his observations, and he come up with like a routine or mathematical equation that fundamentally depend on the distance from the shaft, the excavation depth, and also depend on the soil type and the width, like the diameter of the excavation, and some empirical factors that depend also on the construction method and the soil, to come up with like the size of the ground and the depth of or like the value of the settlement relative to the width of this deformation curve. But for other like shapes of shaft or vertical excavation, several methods have been adopted in the literature in order to come up with that. For example, the Canadian Foundation Engineering Manual has employed a method, and Syriat C760 and other method has been explained thoroughly in the literature to come up with that. For example, if we are looking at the Canadian Foundation Engineering Manual, we can see that like the ground deformation curve for the that happens due to excavation can depend on the type of the excavation, or also like our shoring or retaining structure. If we are looking here in the top here, based on the deformation of the lateral support system, we can have a different adjacent ground deformation curve. Therefore, the literature here, and including the Canadian Foundation Engineering Manual, adopted this method to come up with like the deformation curves. So based also like on the type of soil, if the soil is sand, the manual has proposed like curves that we can use it to come up with the ground deformation curve based on the maximum lateral deformation that happens from the wall. If our soil adjacent to the or in our excavation area is soft to medium or like stiff clay, also like there is like a curves that we can adopt in order to come up with the adjacent deformation curve, either like vertical or horizontal. Okay, this is very good so far. We already theoretically know how can we come up with vertical deformation that comes from due to horizontal excavation from tunneling or cavern. And also we can now come up with like ground deformation curve that came from a vertical excavation also. But how can we integrate all of them together? Now, in the world we live right now, it's quite complex because there isn't only one shaft in the area. There isn't only like cavern or excavation in the area. You might find like two shafts, one cavern in one area, and you need now to start to integrate all of this deformation curve together in order to start to study like the effect of this ground deformation on the adjacent structure. So we have excavation 1, excavation 2, excavation 4 in order like to and we have like building somewhere. So you need to superimpose the effect of excavation that comes from one excavation to the other, and then study this overall value of deformation into this building. Now it starts to be quite a complex process because with the number of complexity of different excavation and we have like multiple building, now this start to be like really hard and tedious, something like to do. So there are like some commercial software that you can use in order to integrate the ground deformation curves that come from this theoretical values and create an overall map that you can adopt for your study. Yet it's still based in theoretical calculation. Especially right now, our excavation start to be like really deep, and also like we encounter different soil, different like rock, and like this could be like a starting point to use this theoretical curve, just like somehow have a feeling about what's going on to this adjacent structure. So based on the ground deformation curve that we just had in this theoretical information, now we can start to look how can we conduct like assessment. In order to conduct assessment, generally, like we look at the building as an actual building. So there will be like cracks start to develop within this building due to the excavation. So we look into this building as an equivalent beam, and we start to look at calculate the bending deformation and the shear deformation. There will be like some cracks develop there. Simply, we can calculate the lateral strain, which basically we see how is this building is gonna like move laterally, and this is gonna be based on the integrated maps in vertical and horizontal direction that comes from the excavation. And also we can calculate the angular distortion, which is basically the differential settlement divided by the width of like the building. Based on that, we can start to study or like to assess what is the level of damage that is gonna happen in this building. So after like Sun Encoding has created like a chart. This chart can be used to categorize this damage. We can describe this damage as negligible or very slight, moderate to severe, and also severe to very severe damage. But what does this mean? In order to understand this damage is reflected into the crack width that's gonna happen in this building due to the excavation, and also how much work we need to do in order like to mitigate these cracks. So Berland 1977 categorized these damages and how can we fix that based also like on the crack width. So this is the description of these damages. So Bernard has put also like in order like to based on like the deformation that we already calculated, the vertical deformation and the horizontal deformation that we already integrated from all excavation happening in the area, now we can start to look, okay, how can we categorize that? So Berland, like 1988, has come up with like a table that say, based on the slope that happen in the building and also the maximum settlement that's happening, I can categorize that. Then came some, like as we can see in this table up here. So this is outdated, and came Sun encoding and developed like a critical tensile strain, which corresponding also like to the level damage. So based on the lateral strain and based on also in the angular distortion that we already seen in here that we can calculate, we can categorize this damage. So where we can see say that this damage is acceptable or not, this is basically depend on the agreement in the project that you are working on. And in this project they start to say, like they look at the damage, say like the slight is the threshold that I can like I can accept, or like I will be accepting the damage until like very slight, which doesn't require any mitigation measurement after like the assessment. Or if this structure has been located into like or will encounter slight damage, I would say now I require to do either more assessment, more investigation, or I will be moving to conduct a mitigation measurement, like to ensure that this building will be safe during and after the construction. So this is fundamentally like for like this assessment that we have seen is basically for a shallow foundation, or like building is supported on isolated footing, or like it will impact fundamentally the bricks system, like and the like the serviceability of the building. But what if our building is based on or bearing on a deep foundation? This is like a different story, because now we need to start, like if we have excavation adjacent to a building, that this building is supported on a deep foundation, now it starts to be a bit more complex, because this this foundation of this building will be encountering like different type of failures due to the extra excavations that came from the excavation, extra loot that came from the excavation. So this building, it might or like this foundation might encounter structural failure, either axial or bending moment, or combination between both of them, and geotechnical failure due to the failure in the axial capacity, either in compression or tension. And it also, the soil adjacent to that can encounter also like soil shear failure, and this will also cause damage in this foundation, which will cause damage also like in the building. So if we are looking into this graph, or like in this figure here, we can see that the first failure that can happen due to that is the extra load that comes from the excavation, is a compression failure due to in the geotechnical capacity. This is in number B, this is like a compression failure. Number C, that can happen due to like in long piles, due like buckling having in the pile, or tension failure, geotechnical tension failure that can happen in the pile, or tension structural in the structural capacity in the tensile side. And also we can see in the lower row here that the effect due to the lateral loading that comes from the extra lateral loading comes from the excavation, that can cause either like soil failure or also like structural failure in the pile. So we need to study, like if we encounter like a deep foundations system supporting building adjacent to a structure, we need to look into the axial into like the integrity of like this foundation system. So for the structural failure, for example, we need to look into the interaction diagram based on this foundation system, and to categorize the failure. And the same for the geotechnical capacity or the soil shear resistance. Now, this require more thorough investigation. We can't just look into theoretical equations and we can come up with like this. So now comes the rule why and when we can start to use finite element analysis. Due to the complexity that we have now in the uh, world of excavation or infrastructure from different soil stratification of like the soil, different excavation adjacent to each other, interaction between deep excavation from in a shaft and also horizontal excavation that comes from a tunnel. Now we need like to, and also the different supporting system that for all of them. Now we need to look into more of thorough investigation. For example, we need to conduct finite element analysis where Midas can provide uh, like a great software, GTS NX, where you can conduct an analysis like that based on a finite element analysis. For example, we can conduct like a deep excavation, and we can thoroughly see the vertical settlement that can happen due to this excavation. So, okay, how can we use like the deep excavation here? Like it's quite complex also if we start to create like different excavation in one model plus horizontal like cover in one model, but we still can do that. However, the model might be very heavy, but we also can look into the vertical excavation only that comes from a deep excavation like that, and we can create like a distance like we can create like vertical deformation curve at multiple construction sequence. Like we can see here, I developed like the ground, like the vertical settlement from different construction sequence. With the increase of excavation, we can see that the settlements start to increase, and this is the depth away from the excavation. So how this can be compared to a theoretical one? Theoretical one doesn't take into account all the rigidity of like the shoring system. It doesn't take into account also the different stratigraphy of the soil, and also the complexity that comes from the rising of like or like reduction of like the water level, and many other like factors that can exist in such complex excavation. So we can use an enhanced 3D finite element analysis to come up with like the ground deformation curve and curves either for the vertical and the horizontal direction. And also we can use the same model also to calculate the internal forces in the different structure element, either in the sheet piles, the whaling system, or the anchor. And we can conduct like a design based on the internal forces, and we optimize our design. So there is several benefits that comes from creating like a model like that. First, we especially in a 3D, because it take into account all the corner effect, it takes into account the 3D behavior. Also, you can use like advanced numerical modeling to come up with like the internal forces in the whaler, and also the internal forces in the anchors, and you can perfectly design them. Then you can come up eventually with a ground deformation curve that we can employ into the construction impact assessment, instead of relying on only theoretical values that comes from the literature. Also, we can use the finite element analysis in conduct like horizontal excavation. So we can see here, this is like a connection between a circular shaft and also a horizontal excavation. So we can create this model, and we come up with like the settlement and the horizontal excavation in X and Y direction. And you can also create like the ground deformation, which can be integrated from the vertical excavation, and then you can conduct your assessment. Okay, so one more thing, one more model we can create. For example, like this model present a 3D TBM and like excavation analysis, and from this like analysis, you can conduct a construction sequence. Like the goal of like this session is not looking how to create like this model. There is Midas provide like tutorial for that. I have like tutorials in my YouTube channel for that, and we can go over like how to create this model. But the goal here is like how can we employ the finite element analysis model in order like to create like more enhanced assessment, not only for the design of the excavation, but always also to ensure the safety of the adjacent structure. So from the horizontal excavation like that, we can come up also with the total deformation, which we can create like extract like from GTS NX here. I extracted the ground deformation curve in the top here, and we can have like a nice curve here that can be comparable to the theoretical one that we already looked at the beginning here. So we can see that we getting with like this inverted normal probability curve, or like in another way they call it Gaussian like curve. And now we already have a curve that's comparable to it from the finite element analysis. I just wanted to refer in the theoretical analysis, we basically depended on creating like this graph on the volume loss and the trough width. And these two values, when you start your theoretical assessment, it can be assumed. It can be assumed either from the literature, or it assumed from your knowledge of like the area where you conduct the excavation. But assumption is still an assumption. And in order to enhance the values of the trough width and the volume loss, we can conduct like this 3D finite element analysis. We can come up with like this ground deformation curve, and we can use this ground deformation curve to calibrate a K value, a trough width value, and a volume loss value. Then we can use this like two calibrated values to incorporate them to, or like to create like this improved theoretical ground deformation curve. So far we have seen how can we come with like the ground deformation curve from theoretical equation for the tunneling or like the horizontal excavation, and also from the vertical excavation. And also we have seen that we can employ sophisticated software analysis like GTS NX, using enhanced like modeling techniques, enhanced like soil modeling, in order to come with like more improved or more educated ground deformation curve. And we can calibrate this deformation curve, for example, for the tunneling part, to come up like or to improve the assessment of the theoretical one. So now, so we already now at the level we established that, or we have the ground deformation curve. We already know how can we integrate them together and conduct superposition for all of them to create like a full map for the whole area from the vertical excavation and also the horizontal excavation. So let's think about like what is the routine that I would be using in order to conduct this assessment. Should I rely on the theoretical assessment, or should I just start with like a finite element analysis? Finite element analysis can be a bit complicated, but it gives me the advantage of reliability. So I would say in general, before like either if you have the ground deformation curve that comes from the theoretical or from the finite element analysis, there is a technique, or there is like a series of assessment that you have to go through first, or like we call it like phases. So phase number one, it's we call it the first estimation phase, because if we remember, if we went back here, we said we have like we can conduct the assessment based on ranking, which employ the slope, and the settlement, which quite simple. We can calculate the settlement, we have the slope, and we can conduct that. Or we can rely on the lateral strain and the angular distortion based on sun encoding, and we can conduct like our damage, classify our damage assessment based on that. So what is the steps to do that? First thing, depend also like here we come up with the ground deformation curve, which we have from theoretical or finite element analysis. And then we first thing look into the maximum settlement and the slope. So we look into the first like row in ranking analysis, which fundamentally depend on like classify as negligible. So if my settlement in this building is less than 10 millimeters, and the slope of like the slope due to the excavation is like less than 1 over 500, we say that this is acceptable. However, if it's not fulfilling that negligible criteria for ranking, we assume that this is unacceptable, and we move to a second estimation phase. So what is a second estimation phase? This second estimation phase it depends on to the lateral strain and the angular distortion. Now we need to conduct more calculation to come up with like the lateral strain and the angular distortion. I just like need to emphasize on one very important thing is in the second estimation phase, we're still relying on the green field analysis or like the settlement that comes from the green field, or like I am not assuming any soil structure interaction with the structure. So I'm just like looking at the ground deformation curve due to the excavation and ignoring any uh, stiffening for the soil due to the structure. This is like based on the first estimation and the second estimation that comes from green field analysis, where there is no soil structure interaction so far. So now I'm still looking into this green field. I'm calculating the lateral strain and also calculating the angular distortion, and I'm using the damage assessment curve based on the both values to categorize my damage. In this, like the project generally, the project agreement or like the specification of the project classify, as I said, if the damage is very slight, it can be acceptable, but if it moved to slight, that's not acceptable, and it requires more analysis or more, or like it requires mitigation measurement. However, like we still looking into the green field analysis, so there is no soil structure interaction, and the structure we assume that it deform similar to the ground, but in reality that's not true because of the high stiffness of my structure. Now I would say like the ground deformation curves, it will be also stiffened, and there will be like reduction in the settlement, the slopes, the angular distortion, and the lateral strain. So now, if this is not acceptable based on the green field, we need to go and conduct like the third round or the third phase of this assessment. And fundamentally, it's based on the soil structure interaction. So in the soil structure interaction, we conduct modification for the angular distortion and the lateral strain. But how can we do that? How can we come up with like this modification and like the stiffening into this the stiffening of like the ground deformation due to the structure? There are also like theoretical work has been done to account for the soil structure interaction in the tunneling. One of the most famous one is is 1997, where the study assumed that if we have a building in top of a tunnel, and they have conducted like a really big numerical modeling and come with like many factor. Eventually, they come up with like some graphs that provide factor that conduct reduction for the angular distortion from the free field analysis for both the angular distortion and also the the angular distortion and also for the lateral strain. Based on the modified values for the lateral strain and the angular distortion, we can again go and visit the graph here, and we conduct and we classify this damage. But realistically speaking, in a building which that will be like a very complicated also process, but this is now we're still looking into the tunneling. So now let's move to how can we conduct like a soil structure interaction based on the excavation. Now it gets even more complicated because now we have to look into this building into in terms of like beam, or equivalent beam. We come with like the equivalent bending moment and the equivalent building stiffness, Bearson and Cording, and his paper has put like a step by step like how to come up with like soil structure to account for the soil structure interaction from the building and also like the soil, and update that into the graph for the classification. Okay, now it start a bit. There is like something for like the excavation. There is also like something for the tunneling, and this is like start to be complicated. How to integrate that together? This is when we say like it's a very complex process, and when we reach to this point, it's preferable like to conduct either a modified finite element analysis to update the curves, or to conduct like a full 3D soil structure interaction analysis between the building within the excavation to thoroughly study like the effect of the excavation on into the building. So in order like to have like a roadmap, like this roadmap to show us where we can start and where to go. Like I would say, the first round in when you are conducting a soil structure interaction, you can depend on a simplified method because in the early stage there is no design yet, and maybe one of the requirements for the project is to come up with like an assessment for the adjacent structure. So the theoretical the theoretical analysis that comes from the method that we have already discussed, we can use them in order to come up with like an assessment. This is like the ground deformation curve due to the excavation. We can integrate the excavation or the ground deformation that come from the vertical excavation and from the horizontal excavation together in one big map of settlement and lateral deformation, and we can conduct a free field deformation analysis for phase number one and phase number two. So let's again, like we have like round number one, it depends on the theoretical analysis, and we will conduct phase number one and phase number two. So what's phase number one and phase number two again? It's like when we are looking into the settlement or from the green field and the slope, and then we assess based on Rankin and the negligible one. If it's okay, then we would say that this building most probably is not going to experience any damage. And if it's didn't pass like the criteria for ranking, we go for like the second round, which the second phase, which is the based on the angular distortion and the lateral strain, we classify the damage. Then we if like the building didn't pass the criteria, then that's good. And if the building didn't pass the criteria, I would say we go to round number two. So what's round number two? We move like the building from this simplified now to a better assessment. Mostly we start our excavation was conducting like a 2D analysis if we are assuming that our excavation in a plane strain behavior, or like axisymmetric if we are looking into a circular shaft. You can use GTS NX to conduct a 2D finite element analysis, and you can come up with like a ground deformation curve adjacent to the vertical excavation, or you can also calibrate your Gaussian curve based on the trough width and the volume loss to come up with also the ground deformation due to the tunneling, integrating them together in one map that takes the account of the vertical excavation and also the horizontal excavation. Now we already created like more advanced or more enhanced ground deformation curve. Then we conduct the two phases again. The first phase, now because this is still based on the ground deformation curve. In the second round, we still didn't add the structure yet. We still just simulating the excavation from either vertical or horizontal, and we are coming with like a free field or a green field ground deformation curves. We go back again to the same flow chart that we are conducting for the damage assessment. So we are looking into the first estimation, which is based on the settlement and and the slope. If it's not passing ranking, we move to the second line in the flow or second phase in the flow chart based on the lateral strain and angular distortion and classify the damage. So now, if the building didn't like pass the criteria for the second round, where I'm depending on a finite element analysis in a 2D or axisymmetric analysis using like GTS NX, for example, like we can now move, like we can either like conduct like an enhanced assessment as we're simplifying the building into a 2D analysis, and just like to start to see, which sometimes it get to be like it's either simplified or approximated, or we can conduct a mitigation measurement here, or we can move. The third option here is like you can move like to the third round of the assessment, where you conduct a full 3D finite element analysis, assuming the existence of the superstructure and also the existence of the soil and the excavation. You can conduct this analysis in like for the part of the superstructure in a structural software, Midas Gen, for example, and you can export the good thing that the compatibility between the Gen and the GTS NX is that you can export the model and the result from the structural analysis one to conduct like a full superstructure structure foundation interaction analysis with the soil, and now you can see the effect of the effect of the excavation into onto the building and its foundation using GTS NX. So in this like round, it's very important because like in the second round or the third round, although like they provide like very great assessment because now we are relying on a more enhanced calculation from the finite element analysis. And also this if we encounter there is like a building adjacent to the excavation that's supported on the foundation, now we can start to calculate the structural forces that would be resulted from the extra load from excavation, and we conduct like more thorough assessment for the structural capacity, also for the geotechnical capacity and the soil resistance in the area. And based on that, we can start to have like a better assessment for also like the deep excavation. So now we already understood that like how can we calculate the ground information from theoretical analysis, from finite element analysis using GTSNX, and now we are adopting a flow chart that tell us to when we depend on a flow chart that tell us like you can depend on the first round of simple calculation on or a green field based on Rankin. Then if it's not passing, you go to use Sanan Cordon based on the lateral strain and the angular distortion. And that in the first, and you can use like three also round of analysis, the simplified one at the beginning of like the project, and you don't have like a finite element analysis model that's ready yet to be used, and you can enhance your assessment based on using a 2D or axisymmetric finite element analysis like GTS and X to provide like more enhanced ground deformation curve. And if you're still encountering a problem in the building adjacent building based on the flow chart, you can move to conduct a full 3D finite element analysis. And now you covered the third part of the flow chart, which you account for a 3D finite element analysis. And the good thing about like conducting a 3D finite element analysis is you can also simulate the building, and when you or like the adjacent structure, and you have more enhanced assessment for the whole area. So we can see here, like we can conduct a superstructure interaction from the using like Midas Gen, and I imported like the result from Midas Gen to Midas GTS NX and conducted like a full superstructure soil interaction analysis. To summarize, what we wanted to come up with like this assessment is ground construction impact assessment is a very crucial component of any project. Like it's very important to support the excavation and make sure it doesn't fail. But what's also really important is like to ensure that the safety of the adjacent structure is also okay, and there is nothing will jeopardize its integrity. Like it's not gonna crack, it's not gonna fail, and we are saving also like the life of the people around. The second thing in this from this session is the assessment reliability is mainly depend on the ground deformation curve that result from the construction work and also from the background information. Two components are very important in this assessment is when we are looking at the background information for the adjacent structures, it's we need to have like a full understanding of how the adjacent structure has been built, its foundation system, the depth of the foundation, does it have basement or not, where is the ground level, what is the type of the soils in the area. So you need to have like what is the load that has been used for like the design, the usability of like the building itself. So a lot of background information are very important when you are conducting a construction impact assessment to understand the adjacent building. And the second thing is the ground deformation curve. Like when it comes from a theoretical assessment, we have to understand it's theoretical, it's also approximated. It might overestimate the ground deformation or underestimate the ground deformation, but still a good way to start to do the assessment, but we can't only rely on the theoretical one. We have to conduct a finite element analysis uh, in order like to strengthen the reliability of like this structure using a 2D finite element analysis or axisymmetric analysis that will give us like an improved ground deformation curve to conduct our assessment. If we still encounter problems, if we still encounter problems in our assessment, we can move to a full 3D finite element analysis and we can explore different options, constitutive models in GTS NX to have a better understanding for the soil and also for the foundation system. In this session, we have presented a procedural system that we can use in order to conduct the construction impact assessment, which is the 3 steps of the first estimation based on the ground free field analysis and based on Rankine settlement slope. The second one is based on the lateral strain angular distortion, and then the third one is based on the solid structure interaction. And we have discussed also the importance of using finite element analysis and the combination with a structural software like GTS NX with Midas Gen in order like to come with like a full solid structure interaction model that can enhance our assessment in terms of like shallow foundation, also very important in terms of we have a building that's supported in deep foundation. So that would like take us like to the end of the session. I think I am good in terms of like time to have like some minutes for questions.
Thank you, Ahmed. Yes, we have a couple of questions. The first one says, does critical strain assume a certain building material? Oh, I think. Oh, I think he clicked the wrong button. Please give us 1 minute. Let me see if I can get him back. There he is. Okay.
I'm sorry, like I just like
No worries.
corrected my mistake.
No worries. Okay, so the first question we have asks, does critical strain assume a certain building material?
Does critical state assume
A certain building material.
building material like in like a critical state of you mean like to say that this building is critical or not? I just like need elaboration on the question.
Critical strain, not state.
Oh, critical strain. It depend on the type of the structure that you are assessing. For example, if you are assessing not only building, because in this type of assessment we also assess the utilities in the area, either hydro or sewer or whatever utilities that we are using. So based on the utility itself, or based on the we say that like this is level of strain is acceptable. But for the building, we are assuming that this level of strains is based on a brick, the brick of like the structure, because we don't want them to crack. For the concrete, we are assuming that in this assessment that the concrete will not crack, and it requires more thorough investigate like a different kind of investigation if it's not passing. So this level of assessment, it's first of all it look into like if we're looking at like a building, it's into the bricks of like the building. So the concrete is not gonna crack before we can see like cracks that's happening in these bricks. But in the utilities, yes, because the utilities like has like different material, concrete, bricks, verified clay. Yes, we fundamentally like base that on the level of the strain.
Okay, the next question asks, how far away was the building exactly? Sorry, how far away was the building from the excavation? Um, and did you check the settlement?
Yeah, that's a very good question because like when we are conducting this assessment, we first of all look into creating like the zone of influence, which means we see like how far due to our excavation uh, like this the area will be affected. So the project decide what is the zone of influence based on which level of settlement. Some projects employ like 5 millimeters is this is the project zone of influence, and all the structures inside this project zone of influence I start to look into that. Some other project would look and into like 1 millimeter would be like our project zone of influence, and all the building inside that will be inside that will be studied. So I have to review, but also there is like a third option here when you are reviewing the project requirement, that some project would say that okay, like all the building and all the structures, including the utilities or streetcars or trains inside the project zone of influence will be studied, plus any other structure outside of the zone of influence might experience failure. So it depends also in the importance of like the structure itself. So like some criteria here. First, I come up with like the zone of influence, which it comes from the theoretical one, theoretical calculation first. So I develop a zone of influence where like the structure and I study the structure inside that. Second, then I enhance this project zone of influence based on numerical analysis. So I refine this zone of influence based also like in the settlement that we working with, if it's like 1 millimeter or 5 millimeters, then based also like in any structure that might encounter any problems, we also account for that.
Okay, the next question asks, how long did it take you to run each model, prepare input, and run it?
It really it really depend it really depend on the model itself, because like the models that like I'm presenting here, for example, it's like an example of like, let's say 15 meter of excavation or like 20 meter of excavation. So it really depend on the model. It depend its complexity. So right now we are working like, for example, like on like on a shaft. If you are looking at this shaft, it's partially could be like in like in soil, partially it can be in rock. That's like two different like supporting system. You can start with like the type of the model is 2D, the type of model can be like 3D. If you are accounting also for the horizontal excavation in the model, so it really depend on the machine that you are using, like the computer you are using and the number of processor you accounting for it. So this is like a really relative question. It really depend. Also it depend on how you are refining your model, or like the level, like the type of the mesh that you are using, the number of nodes that you are using. So there are like really many variables that it can to account in order to say that like this is the time of the run or not. For like the time to create like the model itself, it's also depend. It can be like from range an hour to like to a week to a month, like to make a model and run it. So that's why we are saying we are looking at something like a project like that, or like this type of like work. We start with like theoretical thing, like to have like a feeling where you are, then you move slowly to use like the finite element analysis and build a model.
Our next question asks, can this type of analysis be used for concrete dam design?
This type of analysis used for you mean the assessment or the analysis? Like the type, like this kind of assessment or the analysis?
I
I
assume the
would assume, yeah,
analysis.
I assume, no, I think like I assume the assessment, like the procedures of this assessment to be used for due to like dams. Uh, like generally, let's look at that. As long as you are following like what's happening due to the construction, like we see that we are categorizing this assessment is based on the cracks that might happen in the building. So as long or like in the structure. So as long as you are reaching to the level of the foundation, and uh, you are like getting like the lateral strain under it and the angular distortion, you can conduct like the same assessment. But if you are looking into the theoretical calculation, of course, like this is different like analysis. If you are encounter like if you are using dams. So I also like for like the dam safeties and like I don't really think that it there is like different structure like around it, and there is other like things which should be like taken into account when you are like studying dams, like including like a rapid drawdown that might happen, like so that it's like a different story when we are looking at dam, like different type of failures. But if we are looking into the assessment itself, as long as you are having the protocol of like the lateral strain, like the angular distortion, you can use a graph to categorize like the damage.
Okay, the next question asks or states, you reference the new 2017 circular shaft. Who is this authored by?
It was authored by New 2017. You also may like send me like an email. I can send you like the reference. And also like this is just like an example. There are other like paper, because like just like to refer again, like this study that was based on an investigation that happened in UK during like the construction of the shafts in the Heathrow London Airport. So this like you might find like other studies that have done like and have observed like different things, because like if you remember from the calculation itself, it's based on like different factors. This different factor, it depends on the diameter of like the shaft, it depends on the depth of the shaft, it depends also in the type of the soil within the area, like to know the like the settlement and the width of like this. Even inside like this paper, like I remember when I read it, like they were referencing other paper that has done a similar study on a different type of soil, and they had like different factors for the and like the alpha, if we went back to the same equation, which basically depend on two factors in an alpha, like they adopted like specific values in this area, but in a different area they adopted like totally different values.
Okay, and the last question we'll take today asks, did you compare the results between Plaxis and Midas?
For this project specifically, or for like this work, no, I have not compared. In reality, like they should be both producing similar result. Uh, so I'm not expecting really, if I have conducted excavations, that I would be having like that significant difference between the two softwares. So I would say like Midas is like a great software, will produce that. Lexus will be also like producing also like a similar result, more or less. But like I would look into the software from like a different perspective. First of all, it serves like a purpose. Uh, like when the software is like, or when the model is a bit complex, like I have a preference when I'm picking like the software. Like I need like something that can give me like a bit more of flexibility to create like things that I can't create. Like I would say I would be using like GTS NX, for example, like if I'm having like a big model, like, and I want to have like more control in the meshes, or like I want to have like more of like use like more on hand on building like the model, I would be using like a software like GTS NX. I do believe that it will give me the capability to like to build like this model easily in such a way. Uh, so yes, like at the end of the day, like if answering the question, I'm not expecting any difference if I'm creating like a similar model in the two softwares. In the past, in a different in different structures, I have done this comparison. They produced similar result. I was at this time studying the bearing capacity of foundation, like it was just like a simple model, and they literally like produce similar result. But like yeah, it depends really on in many things, like when you are picking your like the software.
Okay, that's all the questions we have for today. Thank you so much, Ahmed, for today's webinar. We had a really great turnout, and I know everybody really enjoyed it.
Thank you very much, Luciana. Like, thanks everyone for listening.
All right, we will send out the recording probably tomorrow morning, so everybody can
Awesome.
look out for that. And thank you again, everybody. Have a great day.
You too, guys. Have a great day.